He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
Maybe tens of the 5,000 planets we know are anywhere near like Earth. And so we know now that it's really, really rare.
But sometimes what we see in movies or read in books is so incredible, it obviously couldn't be possible. Or could it?
A lot of people have been sitting down and trying to think about this very hard. What the aliens would do and what we're trying to do to try and see what we would term those biosignatures in the spectrum to actually say, there could be life there. Because even if there could be life, who knows what could be there.
Welcome to Sci Fi, Sci Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have.
Space. The final frontier. These are the voyages of the Starship Enterprise. Its 5-year mission: to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no one has gone before.
Welcome to Sci Fi, Sci Fact, our little discussion that's at the intersection of science fiction and reality. And here to tease out the plausible from the implausible this week is Jan Eldridge from the McDiarmid Institute, also Associate Professor of Physics at Auckland University. Kia ora, Jan. Welcome back to Sci Fi, Sci Fact.
Kia ora, Brian. Good to speak to you again.
Your topic, exoplanets, or why does every planet in science fiction look just like home? I mean, what are the odds of that, right?
It's extremely rare. I mean, it's worth noting back in the 60s and 70s, we really didn't know because we only detected the first planet around another star in 1995, I think. And it's taken us decades now until we know about 5,000 planets around other stars, that things that are in Earth's orbit around its own star are really rare. I mean, we don't know if there's life on these planets yet, but there's like only a handful, maybe tens of the 5,000 planets we know are anywhere near like Earth. And so we know now that it's really, really rare. We
know of 5,000 exoplanets.
Yeah, we hit that just a few months ago.
Okay.
So it's quite a thing to actually get that large number, because it's like we know so much better about what type of planets there are out there.
Congratulations, astronomers. What was the first planet discovered and where is it?
So the first planet around a solar-like or a sun-like star was 51 Pegasus b. And that was a really unusual planet because, we were developing a technique to actually try and develop these planets. And what you're actually looking for is you're watching the star, and whereas the planet will go around in a big circle around the star itself will go in a little wobble back and forth. And you're trying to pick up this star moving backwards and forwards at tens of meters per second. So something that's still a little bit faster than running pace. And that's what we're trying to pick up as the planet orbits around. And we found this gas giant that's about the size of Jupiter, but really close in. And it would orbit the star in a matter of days. So we call it a hot Jupiter. And these are the main kind of planets we find now, that most of the planets we know are hot Jupiters because they're massive Jupiter and really close into the sun.
And therefore they create quite a lot of wobble in the star that they go around.
Precisely, yeah. So they're the ones that are really easy to find. But as we go through and we're trying to use other techniques to find planets, we're finding that they're not the main type of planet out there, but they're certainly the ones that are easiest to find, just because they're big and they orbit their star so quickly.
So if you had a gas giant, and when you say close to its star, is it as close to its star as we are to ours?
No, a lot further in. So it takes something like days or weeks to go around its star. And of course, we take 365.25 days to go around our star.
Really?
So these things are really, really close, much closer than even Mercury is to our sun.
Wouldn't the gas giant kind of have its gas blown away by the nearby star, its solar wind?
Well, if they're that massive and that big, the chemistry of these planets and actually trying to understand them is really, really interesting. So yes, that's a very good point. And so they are not going to be anywhere like our Jupiter, and maybe they have lost a lot of mass, maybe they're slowly evaporating, maybe slowly they're drifting in towards the star itself, and one day might get swallowed by the star. There's lots of things we don't know about this, but we can see that they're definitely big, they're definitely there, and we know they're very different because they're so hot.
Now, this planet was discovered, and if you could see me, I did some quotation mark things on either side of my shoulder just then, because the thing is, we didn't actually see it. We just saw a wobble in the star it goes around and said, aha, that's a planet. Now, we can be pretty confident that we're right about that, but have we actually seen it? Actually seen, a tiny little speck in a telescope anywhere?
So this is something that's we're now starting. Now we've got these 5,000 planets. It's difficult. It took us centuries of astronomy trying to work out how to do things to detect planets. Now we're getting to start doing more exciting things. So there are some planets, a literal handful that we've detected directly, but they are actually quite the opposite of these hot Jupiters. They're Jupiter mass or gas giant sized planets, but very far out. But the more exciting thing is that if you have one of these planets that transits or goes in front of its star from our point of view, we can actually try and not image it. We can't see it, but we can see that the light from the star gets dimmer. And so actually this is how we detect close planets, by this transit technique, because there you're not seeing it, but something's gone in front of the star, and it's going in front of the star every week or every so many 100 days or something, and you can say, that's definitely a planet because it's blocking out its light. And the most exciting recent developments is that we're getting really good at what we call transit spectroscopy. So you take a spectrum of the star, you spread out all the light into the colors of the rainbow of the star normally, and you compare that to a spectrum of the star when the planet's in front of it, and you can actually try and detect the atmosphere of that planet. So you're detecting the gases in the atmosphere. So that's why we know these hot Jupiters are kind of similar to Jupiter, because we can see that it's made of the same sort of stuff, but of course a lot hotter.
Because our planet Earth scatters a lot of blue light. The atmosphere scatters a lot of blue light, doesn't it? I assume because of the nitrogen and oxygen mix that dominates our atmosphere?
Yes, that's why actually when you're doing this, you need to go.
Or is it water vapor? Is that H2O as well? I'm just thinking, we do scatter blue light. And if you were an alien civilization looking for Earth, and you're, I don't know, a few dozen, maybe 20, 30, 40, 50 light years away, and you look at the sun and we transit the sun, our sun, and would they see a little bit of a telltale sign of maybe a bit of extra blue light being scattered, and they could say, that's an interesting atmosphere?
No, so the blue light scattering is something that only we really see on the ground, because that's the sun coming in. So this is more like the light. So the thing is, the sky is blue because the light is being scattered in all directions. So if you actually wanted to know what an alien civilization might see, then you've got to think about when there's a lunar eclipse, because there the moon goes into our shadow and you see it turns deep red. But the red light isn't enough. You actually have to do it in terms of looking for these emission lines which are coming from the molecules that we know about, or the atoms. So when we're doing this transit spectrometry, we're looking for things like hydrogen and helium and ices of water and carbon monoxide, and even rocky things like iron, magnesium, calcium, sodium, which we've detected some of these things around other planets. But detecting things like oxygen is hard because it doesn't have a really strong spectral feature. And a lot of people have been sitting down and trying to think about this very hard. So what the aliens will do and what we're trying to do to try and see what we would term those biosignatures in the spectrum, to actually say, there could be life there, because even if there could be life, who knows what could be there. So the blue scattering is a good thing, but many atmospheres have scattered blue light. So yeah, it's tricky.
Right. So what are the telltale signs of oxygen in an atmosphere using spectroscopy?
Well, it's difficult because it would be quite a broad line at a certain wavelength, because we can check this. We can go and get some oxygen, put it in a test tube, and shine a light through it and see what lights get absorbed. So we understand all these features really well. But what's confusing, and if I remember correctly about oxygen, is that there's all these other lines in the same region, and also they're probably in an area that from our atmosphere is really difficult to try and study. And for the rocky worlds we're really interested in, i.e. the Earth-like worlds, the problem is they're really small, and also there's not much atmosphere compared to a gas giant.
Which is which is kind of a gas giant, is really mostly atmosphere, isn't it?
Yeah. Precisely, yeah. So it's much easier to get a signal for those. But this is going to take time. So the JWST, the satellite that, or the telescope that NASA launched a few months ago, that's in space. It's got infrared spectroscopy on board. So it's really going to be able to start looking at these things. But it's always the problem that you said earlier on. It's that, we detected this planet, but how can we be certain? It's going to be even more difficult when it comes to finding oxygen around other stars. And you've got to think back when we was in the 1990s, when we were starting to detect planets. It was like we would detect them, but then they would go away because people said, no, it's not actually a planet. It's something else to do with the star that we've misunderstood. So again, we're in this phase where we're in the exploratory phase of trying to do this stuff, and we'll get better with time. And so come back in a decade time and I'll be able to say, oh, we know all these planets have oxygen. Whether there's complex life there or not is another entire thing. And that's difficult to find out.
Obviously, the sensitivity of the sensing apparatus must be remarkable, because how far away can we look, and how big are the stars that we are looking for evidence of a planet transiting across from us?
So I went and looked up in terms of the distances, and it's like we're talking most of the stars we know most of the planets we know are all within about 300 parsecs, which is about 1,000 light years. And we know of stars much further away than that. But when you're starting to get to hundreds of light years, that's much, much fainter than the stars in the night sky. Now, our modern detectors are exquisitely sensitive. And one of the reasons why astronomers keep going to governments and say, give us billions of dollars so we can build these big telescopes, is that we can collect more light, especially if you put them in space. Because actually, one big problem with all of this atmospheric work is that we've got our atmosphere between us and that other planet.
The one that scatters all the blue light.
Exactly, and that's got a lot of oxygen. And actually, the worst thing is it's actually got all this water in our atmosphere. And it's actually water which makes infrared observations really hard from the ground, which is why we have things like SOFIA, NASA's 747 with a telescope in the back of it, because it flies right up in the atmosphere above all the water vapor, or you have to go to space. But the instruments have to be really, really sensitive. And the way we do it is we've got to stare for a very long time at that star because it's so far away. If you stare for longer, you collect more light. But of course, then you've got the other problem that the transits don't last very long. They might last a few hours. So you're limited not just by the distance of these objects, but for how long you can stare at the star before the planet goes beyond it and starts going around its orbit. And you have to wait another few weeks or days before that planet comes back across its star.
And what is the largest telescope we have in space at the moment, Jan, that is looking for exoplanets?
So in terms of looking for exoplanets, there's actually a bunch of very small ones. I can't remember their exact size, but they're small, which means they're cheap and easy to launch. And one is called TESS, which is like taking basically a movie of the night sky, because this is how we really find most of the planets, just by looking for them, the little dips we see in their brightness. And we're talking, when I say a dip, I mean something about to a fraction of a percent. So you're seeing the light from the star, which is quite bright, right? If you think how bright our sun is, it's outputting on the surface of the Earth about 1,000 watts per meter squared, which is a lot of energy. And if you go right up to the sun, that's a lot of light. But the sun will, if you're an alien looking at the sun and you see the Earth go in front, the brightness will dip by about 1/10,000th of the total brightness. And so you need to be really sensitive to actually pick that up. But you've also got to be taking fast time observations to actually see the dip. So trying to actually find exoplanets is difficult. The biggest telescope that we will be going and following up on those exoplanets with is JWST, because that's a 6.4 meter telescope, I think, which is pretty big. Not the biggest telescope we've got, but it's the biggest one in space.
You mentioned we know of 5,000 planets at the moment, exoplanets. But of the stars that we've seen planets around, that we've sensed, how many more planets might we have missed?
Well, current estimates suggest that every star in our galaxy has one or two planets. If you're just looking at a sheer number game, so there's got to be hundreds of billions of planets in our galaxy. And there's a huge variety when we look at these different types. It's actually, what's interesting now is we're finding different types of planets compared to those in our solar system. In our solar system, we have the terrestrials, which are rocky planets like Mercury, Venus, Earth, and Mars. I've got to get these right, otherwise I get in trouble. And then you've got the gas giants, which are Jupiter, Saturn, Uranus, and Neptune. Now, as I've said, we've talked about the hot Jupiters and the hot gas giants. We found that there are things called super Earths. So they're rocky worlds like Earth, but about 10 times bigger, either in mass or in radius. And so it's like, how can you make something that big and be so rocky? Because we don't have one in our solar system. So something is different in the way that solar systems work. So it's quite exciting to think that there's stuff we don't understand about planet formation, and we're learning that, which is kind of cool.
As you pointed out at the start of this, when we were first creating science fiction, we didn't know of any for sure, but now we do. But here's the killer, Jan. All the exoplanets that I've watched in sci-fi movies, and most of the ones even that I've read about, all are just like Earth. And you know, what are the chances of an exoplanet that's like us, where you don't even have to put on an oxygen mask and a tank, or you don't have to worry about the change in gravity? You can just get off your spaceship and go to the dairy and buy some beer.
Yeah, if there's a dairy. Yeah, so, I mean, so I once went and watched Doctor Who and counted the number of Earth-like episodes where they actually end up on Earth or Earth-like worlds. And you're right, it's surprisingly common. And it's like in the original series, I think it's only about 10 or 20% of the time, or in the current series as well of Doctor Who, only 10 or 20% of the time do they go somewhere that's quite alien to Earth. And part of that is because you're studying the story of humans. And so you would expect us to go to places where we could live quite easily, you know. And there's this concept within science fiction of terraforming, which is basically where you get to a planet and you make it like Earth. So then, you know, you don't need your spacesuit. I mean, the reason they did it in Star Trek and in Doctor Who is because it's cheaper to have your actors run around in the local park rather than sending them to build a set. But no, we shouldn't be unfair, because if you watch the early Star Trek and Doctor Who, they do go to planets where you need spacesuits to actually live outside. I mean, it's not completely.
I just can't remember them. I can't remember them. I just remember the different coloured suits. If you had the wrong coloured suit, you were just an extra. You were going to get wiped out before the end of that episode.
Yeah, precisely. Because they changed the colour now. Apparently, it's gone from red to blue. If you're watching Strange New Worlds.
What am I doing in this blue suit? I don't want to be in a blue suit. Yeah. Give me out of this blue suit. Sorry, Jane. Anyway, I've interrupted. We were talking about, okay, Star Trek, some of the worlds you did have to wear an oxygen tank, carry an oxygen tank and wear a mask to survive, right?
Yeah. And so there's actually a classic episode where they're stuck. It's a prison planet, and actually it's a really good place to put a prison planet. If you don't want the people to escape, you put them on a planet where if they go outside the space station or the prison, they die. And so there is this scene where they go outside in spacesuits because, you know, otherwise the two people would die.
I mean, another obvious reason to have the same mass as Earth, obviously the atmosphere, because if they've always got masks on, I mean, you know, half a drama is somebody's facial expressions. An actor can't act if you can't see they've got a mask in front of you most of the time. And then there's the whole, if you were to be realistic about their gravity, these various exoplanets, sometimes they'd be getting crushed, and other times they'd be leaping up and down like they did on the moon, which was fun for a few minutes, but you get bored with that after a while. Whereas if it's just all like Earth, it's so much easier and it's probably cheaper.
Yeah. Well, then there is an episode of Doctor Who when they're on the moon, and it's Jamie goes off and has fun jumping around on the moon, and he knocks himself out when he lands because he didn't realise it's a completely different thing, and he landed awkwardly and knocked himself out.
You know, Jane, that reminds me of my favourite scene from, is it A Grand Day Out? Wallace and Gromit? You know how they arrive on the moon, which just turns out to be made of cheese, and they've got a ball, and I think Wallace kicks it up in the air, and it never comes back. And I love that scene. Yeah. But
if you want to break your record for your best golf drive, definitely go to the moon. I don't know if they ever. I can't remember which American astronaut it was, but he did take a golf ball and swing it, and I can't remember what the distance was if they ever measured it. But yeah, you can definitely do that.
Was he able to go and retrieve it? It might have been too far.
Yeah, because they've only got so long they can spend outside of their spacesuits. But I mean, you see that in some space movies where they do have this thing about their oxygen running out, so they're always commonly thinking about it. Although actually, if I remember correctly, the issue is not so much using up your oxygen, it's more getting rid of the carbon dioxide, because that's always the issue which you actually see as well in Apollo 13 because they're in that spaceship going to the moon. They don't get to land, but they run out of carbon dioxide. So yeah.
And there you, hats off to Ron Howard in Apollo 13, does have zero gravity scenes, and also Stanley Kubrick in 2001. Okay, it wasn't a planet, it was the spacecraft heading towards Saturn, but at least it was zero gravity. They did do that, and that was part of the, I guess, the spookiness and the brilliance of the movie.
Mm. Yeah. Yeah, but you're right. There's very few TV shows that actually show the heavy gravity because it would probably be pretty boring actually because the person would just basically sit there. Although if you go and read books, for example, you can see that there is this discussion. There's this common theme going through that, if you grew up on a heavy world of heavy gravity, then you get your people are shorter, but they're also stronger because they have to move around, and so then they go to like a lighter gravity world. And they can move around a lot easier. And then the reverse is true, that if they're on a lighter gravity world, they will tend up being taller. I mean, I don't know if that's actually true, but it's probably true. But until we actually do go and try and live on these other worlds, we don't know. The one other thing that if you actually are a species that grew up on a heavy gravity world, you'd probably actually have a really strong fear of heights. Because unless the bones were made of different material, any fall, even maybe if you're just falling off a table, which can be serious even on our gravity, but if the gravity was like 50% or even twice, you could get quite seriously injured. So in novels and other things you do see this, but it is funny. That's a really good point. I've never seen that before in other things. You normally see it when the rocket ships are accelerating and you see the G-forces, but not just from being on a bigger planet. That's a really cool idea.
You'd have to have tiny steps, and anything that fell off the table was gone burger.
Yeah, but it would really hurt your foot, probably break a few toes.
Yeah. What then? Okay, there's plenty of reasons why sci-fi would want worlds that are just like ours. The question is, what are the chances of finding a world? What's the closest we have found to Earth, both in terms of its mass, its size, actually more than both, also in its atmosphere? What's the closest we've found, and where is it?
So the atmosphere, I'm pretty sure I can say that there's nothing with an Earth-like atmosphere yet. We've detected water ices in atmospheres, but they're not, as far as I know, actual real Earth-like worlds. There are lots of, so this is always a problem. We always have to, when we're teaching first year astronomy, we always have to be really careful about describing it, what we mean by Earth-like, and is it habitable? And that's one very different thing, because the second I say a habitable world, everyone thinks oh, we can go and move there and it's got oxygen, so it is exactly like Earth. What we can tell so far is we can tell that we have some planets that are orbiting their star at a distance, which means you can have liquid water on the surface. And so in our solar system, that's just outside Venus's orbit, out to about Mars's orbit. It's a very big area because, any planet within that regime gets enough energy from the sun to heat it up, to keep it warm. And I mean, to have a greenhouse effect, which actually even our planet has a normal greenhouse effect. Yeah. Otherwise, we'd be 20 degrees.
We'd be much, much colder. We would be, not a very nice place without the greenhouse effect. It's just, imagining it.
Yeah. So a lot of the uncertainty in that is actually to do with what the atmosphere is and what kind of atmospheres you can have on the worlds that can give you those temperatures. Now, we can also tell the size of these things, especially if they're transiting, so they're going across the face of the sun, because there we can actually literally measure their size, and we can have a good guess of what they're made of and what their density is from also watching the star, seeing if you get the same wobble as well. But,
in that case, what's the close? Just looking at mass and size, what's the closest we found? Anything that is Earth size and mass?
So if I remember correctly, there's a planet going around one of these stars in Alpha Centauri, which I think is Proxima Centauri, which is the closest star to Earth. That is, I think there's an Earth-sized planet in the habitable zone where there could be liquid water. There's also another super Earth, I think, which is further out. So it's actually the closest star in the sky, which you can't see with the naked eye because it's too faint. But the closest star probably has an Earth-sized planet in a habitable zone going around its star.
Proxima Centauri.
Yeah, that's right.
What kind of a star is it? If it's that faint, is it like our sun, or is it a brown
dwarf?
No,
so the Alpha Centauri is a triple star system, so it's got two sun-like stars, actually like our sun. They're only a little bit more massive, and they orbit around each other every 79 years. Then there's Proxima Centauri, which is a much more distant. I think its orbit around the other two stars is something like every 500,000 years, so it's much further away from the other two stars. But it's that one, and it's a much lower mass star, so it's much more of a red star. So actually, if you were to look at the light with your naked eye, you would notice it would be appreciably redder than our sun it is, because the lower mass stars, when they're on the main sequence, like our sun, burning hydrogen to helium, are much cooler. And when I say cool, I still mean 4,000 degrees Celsius, so it's like really, really quite hot. But the cooler temperature means it's redder, and you would notice that you'd actually have red light. And of course, the problem is, because it's a lower mass star, it has a different effect on the planet. And so is it more active? Has it got more solar flares? Which I think is a lot of people suggest that Proxima b can't be habitable, probably because of that's the activity of the star itself. But again, we don't know, because it's so difficult to image and try and find out these things for sure.
See, the thing is, Jam, that our planet Earth has an atmosphere that you and I can breathe, but that is a result of billions of years of life evolving and changing the atmosphere. So it's not just that, hey, the planet's in the right place, it's got the right atmosphere. Chances are for life to be there, sophisticated life, okay, I'm saying we might be moderately sophisticated, you probably need to have an atmosphere that's tailored to that life, it's evolved around it, it's changed it and then evolved to survive it, because our early living ancestors breathed carbon dioxide and oxygen was a waste. And now we've evolved to breathe oxygen and breathe out carbon dioxide. So what are the chances of just being able to jump from one planet to another?
Probably very limited. We are linked to the geology of our planet. We have had all life, not just us humans, but all life has had a big impact on the chemistry of our atmosphere and the chemistry of our planet. And that is also linked to our star being at the right temperature, because if you look at the planet Venus, it's about the same size as Earth, but it's closer to the sun. And if you look at Mars, it's a little bit less massive, but also you kind of have to wonder, why isn't that more like Earth? So even within our solar system, you can look at other worlds that, we could in theory inhabit, but we would have to change their atmosphere. Mars has the problem that it's too small. It's got a much weaker magnetic field for various reasons. And so, it'll be quite difficult to try and terraform that. We'd have to smash comets into it. Venus would be much more difficult because it's just got too much atmosphere. It's almost like we'd have to siphon it off, like, using whatever it is they have in Spaceballs, the movie, where they use a big vacuum cleaner to steal an atmosphere. we can't do that, but, that's the kind of thing we'd have to try and think of. So you're right. But it's complicated because there is such a link between the life and the person. It would be unlikely that we could just go and jump to another world unless life had evolved on that planet itself. And of course, then you get into ethical issues around colonization. So if there are other life on a planet, do we have a right as a species to go and move on to that world or not? As a species, colonization hasn't really gone well on the planet so far, even amongst our own selves. So going to other worlds has another problem. And
then there's the issue that life might have evolved very differently under different conditions, and there might be even different ways of, if we are to define life as what? Chemicals, molecules replicating themselves in ever more sophisticated ways and evolving so they can keep on replicating themselves, then it's not necessary that it has to be the kind of DNA that we have. It could be some other kind of molecular structure which might need quite different conditions, might exist in a much hotter environment or a much colder environment. But still, although I guess you could argue that it's possibly going to need water, but what if some other liquid could take the place of water?
So yeah, there's a couple of things here. One is that, water is an amazing solvent. Water, if you actually look at it, is one of the most amazing materials in the universe. Because of the way it can actually interact with other elements. It can be great for doing chemical reactions which is great because our cells are mostly made of water. And so actually, it's difficult to think of anything that is better than water. And people often talk about how you could have silicon-based life rather than carbon-based life. But carbon is wonderful because it can interact again with so many other elements in so many other ways. Now, that's not to say there's only one way of doing carbon chemistry. Now, this questions about what is life and stuff is actually really complicated, and it's probably more than I can answer because it's a truly transdisciplinary thing. You need to actually ask about philosophy. You need to investigate your culture. You need to investigate biology, geology, and physics, and even computer science and mathematics to try and understand what life is. Because at the university, we have a course called astrobiology, and it's taught into all people from all those different disciplines, and we still can't answer what is life. And it's worth noting, though, to taking a step back about, do we know of different life forms on the planet Earth? Are we actually all the same chemistry? No, you're right. We've all got kind of the same DNA, but the two things to think about here is, one is that there are some microbes that we know that are able to use, I think, arsenic in their chemistry, which is toxic to the rest of us.
Yes.
So it's got a different type of chemistry. And the other thing, even taking a step back from oxygen, is to actually think about where life first evolved on the Earth. And that wasn't in the atmosphere. It was deep down in the oceans, by the mid-oceanic ridges, where our the crusts on the plates on the surface of the Earth are spreading apart and magma is coming up, and so they're really hot. And the life first evolved, as far as we know, close to those regions. And of course, they're down there, there's no sunlight. It was just coming off the thermal heat. And so that starts making you wonder, that wasn't based on oxygen, that was just based on thermal energy. And we know of other places in our solar system, especially Europa and Enceladus, where there's other sources of geological heat that are locked under the ice. And actually, there may not be complex life like us, but there may be these kind of very early phases of life on those other worlds, because it's actually what you really need to have energy. You need to have energy being converted into motion and then replication, as you kind of said. And so, that energy doesn't always have to be sunlight, which is where most of our energy is derived from. You can get it from geological processes as well. So all those questions are hideously complicated. And so you need a team of people here to actually try and answer it. And we would probably still not be able to answer it.
However, it's pretty clear that here on Earth, what we evolved from, we needed to cope with the oxygen that we put into the atmosphere, which was initially toxic to life, mutate and evolve to deal with it, and that enabled us to evolve into even more weird and wonderful living things. And so it seems that we are pretty wedded to the atmosphere here, and the chances of finding something that's just like our Earth doesn't look good. The only way I think it's plausible that you could, like Star Wars, jump from one planet to another. One's pretty cold, one's rather hot, one's dry, one's a bit jungle-like, but still, you just jump off the spacecraft and away you go, would be if there's some form of terraforming, that some early civilization colonized all these planets and changed the atmosphere so that you could live on them. And for some reason didn't worry about the temperature or the humidity so much.
Yeah, precisely. And so in Stargate and in Star Trek, there are these concepts of the ancients who were the first to evolve in the universe and basically got lonely. And so they went around and seeded all the worlds. I don't know about terraformed, but if you seed the same chemistry of life anywhere, then maybe the chemistry of that life would interact with the geology of the world and force the geology in a certain way. I don't know if this is possible or whatever, but if you start off life in the same way, is it always going to evolve towards the same humanoid features? That's what you get from Star Trek, and not quite from Stargate. They got other excuses in there.
And
but
also,
you're right. So
I'm thinking down of Prometheus, where the engineers came and seeded life here on planet Earth, and then we eventually discover them, and for some reason, they hate us.
Yeah. Well, we can understand that with all that's going on in the world right now. But yeah, it's funny, and it is that question. One of the biggest questions is, where do we come from? And this starts getting difficult because we're humans and we want to be connected, and we know when they're connected to the universe in the deepest ways because we're made of stardust. All the elements in our body, apart from hydrogen and helium, come from stellar factories that have made those the elements when they've died. But maybe we're alone. If what we're saying is true, and what we're kind of saying is that all these other worlds aren't Earth-like, don't have oxygen atmospheres, they don't have life, then we're alone. And so actually it's down to us to go and visit all those other worlds and try and terraform them, as you say, to try and actually then make it so we can jump around and go to Proxima Centauri B for our holidays, which may be nice. So yeah, it's
unless Jam, somebody terraformed us, and this is what planet Earth a few billion years later has evolved into, and now we're getting to the point where maybe we can find the source.
Yeah. But I mean, so interstellar space travel is still really, really hard. You know, we have trouble going beyond the moon. So it would be difficult to actually go and explore that. And that's why it comes back to astronomy to look at these stars. And it is a big question that, you know, we know all these exoplanets. And you can go to science fiction at this point and say, you know, why are there no other alien species? And so there's some stories, for example, where, you know, there was one that came along and then it just wipes out all other life because it just wants the galaxy to itself. Maybe there's some problem we don't know about. Maybe life evolves to a point where it just becomes sensible to download ourselves into computers. And so then we're just a data program. So we don't need to actually even be able to breathe, you know, which is where our species evolved to be a computational life form.
It leads me to this final question, and that is, given you as somebody who spends a lot of time thinking what is out there, a long, long way from here, what do you think the chances are that there is life out there that we could communicate with?
Now that's an interesting one. So that we can communicate with is difficult because there is something called the Drake equation. It's an equation that came together where how do you work out the number of complex, sophisticated civilizations there are within the Milky Way, and you have to put together things like the number of stars that are being born, how long does it take for life to evolve, how many stars have planets, or how many planets that could host life are there per star, how long does a civilization last for, and all these different things. And now it's interesting because when the equation was put together, we didn't know any of the numbers that we would multiply together to get the number of civilizations, and we still don't know all the numbers, but we know to be probably on the much lower than we would think otherwise. And so maybe within our galaxy, which is quite big, it's like hundreds of thousands of light years across, there may be somewhere between one, we know there's at least one, hopefully, and 100.
Oh, there's definitely one. One and how many?
Some may say a half. It depends if you want to count ourselves.
Okay, let's give us a 0.5, Jan. Come on, let's not hate humanity.
We'll round up to one. Okay, so we've got 1 to about 100 maybe, which means if you work out, it's not like in Star Trek where there's all these life forms within a few light years. You know, you can jump in the Enterprise, go 10 times the speed of light and get somewhere new to tell a new story after a couple of months. This is where it's, even by light speed standards, it's like hundreds of years between the different civilizations, if they exist, which they probably don't. And if we're even more pessimistic, because I think life is probably a lot more difficult to form and start. You know, it took the universe 13.7 billion years to get to this point, and it took our planet 4.5 billion years to get to the point where we are today. So it takes a very long time to get to advanced civilization. And because of that means you've got a low number, and if you've got low numbers in the galaxy, you're very more likely to be distant to the other civilizations you can't communicate. Probably. But it's one of these questions. It's why we get up and try and work out these things, and why we keep on looking at these planets, because I don't think we want to be alone, you know. And it would be interesting to just know that, you know, we're not the only people in the universe. And that's, you know, it's kind of makes it exciting, scary at the same time. But yeah, so I don't think there is a much chance. I do think there must be other life out there, because anything that's impossible enough to happen once, as it has happened on our world, must be happening elsewhere. But it must be quite rare, I think. It must be quite distant. Because the other thing to consider is here, whenever we talk about habitability, we talk a lot about the habitability of the Earth and our sun, and what's going to happen to our future of our sun as it evolves. But we also need to think we actually live within a galaxy, and you can actually think about how habitable our galaxy is. If you go to the center, it's very much less likely to be habitable because you're closer to the central black hole and there's more stars, there's more bad things that could happen to your planet. We're quite far out, so actually, even though we're not completely safe, there's fewer other stars, fewer other supernovae that could wipe off life on our exploding stars that could wipe off life on our planet. And so we're a bit safer, and so maybe all the life form is out on the edge. But also our galaxy has evolved over the history of the universe. So with all this stuff with the Drake equation, it assumes that the galaxy is forming stars and life all the time. But in reality, it may only be, if you do the calculations, as some of my colleagues in the UK have, then if you could look back about 5 billion years, that's roughly when you got a 50-50 chance that your planet wouldn't have its life wiped out by something like a supernova or the black hole at the center of the galaxy feeding and producing lots of X-rays. Which is funny because our sun is about 4.5 billion years old. So it's kind of makes you wonder, is one of the reasons that there are so few people, not just it's difficult to make life, but it's also that maybe the universe has only been possible to have life for the last 5 billion years. And it takes about 5 billion years for life to evolve. We just don't know. And it's all these really interesting questions. And the reason we should be looking for life and trying to contact other civilizations, or at least listening for communications, is because if something happens once, and if it definitely happens twice, then that's something quite deep and profound. And actually just learning about one different type of chemistry of how life could be, for all the questions we've kind of come through in this chat, it would change our understanding of chemistry and be quite exciting.
Thanks for listening to this episode of Sci Fi Sci Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci Fi Sci Fact on the RNZ podcast page. RNZ's podcasts are also available on Apple Podcasts, Spotify and iHeartRadio, or pretty much wherever you find your podcasts. And make sure to follow us so you don't miss out on any new episodes.